All right, so we're going to talk about just domain and range today. So if 7.1 was kind of hard, we did too much at one time, this is when we're going to just practice domain and range. So let's start with example 1. If you think you can do this function, determine if it's a function, then determine the domain and the range. Go ahead and push pause, and then you can watch me do it in just 1 second. So go ahead and push pause right now if you want to do this. If not, here we go. So, vertical line test. So if I put up a vertical line, any vertical line, so if I put up a vertical line, then what I end up with so this vertical line, it doesn't touch over here, but that's okay. When it does finally start to touch, it only touches at most one time. Touches one time everywhere. And then after this, it doesn't touch again, which is okay, as long as it doesn't touch more than one time for any single vertical line. So this is a function. It passes the vertical line test. So let's determine what the domain and the range is. So the domain goes left to right. So left and then to right. So the leftmost that you are. So over here, nothing is happening over here. So I have to move a little bit to the right. And then as I move to the right, stuff starts happening here. And that's at the x value. Remember, domain is the x's. So you're looking on the x-axis to see the x values. That's at the x value of 1. And so since I am a closed circle at 1, that means I'm going to use a bracket for 1. So I'm going to start at 1. Then I continue to go. Everything's good. I'm moving to the right slowly. But then I come to the number 4. And that circle tells me don't actually include 4. Get as close as you can without actually touching 4. So to get as close as I can says, actually, let's write down 4. But if we use a parenthesis, that means don't touch 4. And when I use this union symbol, that means we're going to skip that. And then let's start again at 4, but not really touching it, getting as close as you can. All right, so now we're here. We're after 4, not touching 4. We continue to move to the right. Everything's okay. And then I get to 7, and I have to kind of do that same thing where I'm going to say you got to stop at 7, but don't touch 7. And then since this is actually where we stop, I don't skip 7. It's not like I want to come over here and continue. This is my stopping place. Then I just close my parenthesis, and that's it for the domain. All right, let's do the range. The range is ribbit, bottom to top. So my bottom, so the bottommost I can be, so over here nothing, so my bottom is right here. And that's at -1. And it does show a solid line, so I am going to touch -1. And then as I move to the top, so I'm moving to the top, and right here at 0, I do seem to have part of my function. It's still defined at 0, so that's okay. And I go up to 2.5. And I kind of had to approximate 2.5. I'd make sure on a test or a quiz that that was written on there or something. And there we go. All right, so let's do some more finding domain with function and their equations. So if your function is a polynomial, then what's the rule going to be? Well, first of all, what does a polynomial mean? Let me just separate these spaces. All right, so if our function is a polynomial is just an x raised to some power. So it could be x squared, or it could just be x actually. It could just be x cubed. It could be x to the 5th minus x to the 3rd minus x plus, it doesn't matter. But x's only have their x with some power raised to them. They don't have a square root, or they don't have an, what else could there be? A cubic root or logarithmic or something like that. So if it's a polynomial, then our domain will be all real numbers. This is kind of the easy case scenario, because if you only see x being raised to a power, that means it's a polynomial, so it's all real numbers, which we'd write as negative infinity to infinity. So this is a good example. F of x is 4x to the 7th minus 5x plus 1. That's an example of a polynomial. Therefore, our domain is negative infinity to infinity. Okay? All right, let's do another one. Our second rule. If we have a denominator, then our domain is going to be, now it's going to be restricted. So if we have a denominator, so this is an example with a denominator, our domain will be restricted. And hopefully this makes sense to you, because you know that you are not allowed to divide by 0. That's going to cause the restriction. So what we're going to do is we're going to find the denominator and say denominator cannot equal 0. Okay? So in this example, let's go ahead and check out everything though. So what I mean by that is, look at 4x cubed. Now, if that restricted your domain, you'd want to include that. But as it turns out, that's a polynomial, and so that would have no restriction. Okay? And then we look at 2x minus 7. That's another polynomial. So again, it has no restriction. But then we say, well, even though it has no restriction, it still is in the denominator, and I know somewhere that might equal 0. So I'm going to make sure that 2x minus 7 never equals 0, just because it's in the denominator. So the only restriction we have is created because of the denominator, no other reason. So I add 7, and I divide by 2. So we're saying the only number that we're going to restrict x to not equal is 3.5. It doesn't matter what it is, as long as it's not 3.5. So if you want to think about a number line, that might be helpful. So here's 0, here's 3.5. So I'm saying put an open circle at 3.5. Go after it and go before it, just don't be 3.5. So that's negative infinity to 3.5 union, I'm sorry, I'm going to have to go next line, 3.5 to infinity. So again, that reads open parenthesis, negative infinity, comma, 3.5, close parenthesis, union, and this should all be on one line, open parenthesis, 3.5, comma, infinity, close parenthesis. All right, last one. If you have a square root, your denominator will be restricted. And now it's due to the square root. So we talked about this yesterday. The restriction for square roots, why does that come about? Well, it's because you can only take a square root of 0 or positive numbers. You might be thinking, well, you probably should just say not negative, and that's true, but this is kind of just getting me to the rule. And so what the rule is going to be is that we're going to set the radicand to be 0 or positive, greater than or equal to 0. So this is the radicand, 3x plus 14, and I'm going to set that to be greater than or equal to 0. All right, let's do the last one. So if we put together... Oh, I'm sorry, did I not finish? Okay, so I'm on this example. The radicand needs to be greater than or equal to 0. So the radicand is 3x plus 14. We're going to set that to be greater than or equal to 0. So if we subtract 14 and divide by 3, so we get x is greater than or equal to negative 14 thirds. So the lowest it can be is negative 14 thirds, and I am going to include that, and then I'll go on forever to infinity. All right, now let's do the last one. All right, so the last one. If we put together rationals and square roots, what happens? So if I look at the top right now, it's 3x minus 7, which is just a linear function, so that would have no restriction. Then if I look at the bottom, it's a square root, and I know that square roots have the restriction that they need to be greater than or equal to 0. But not only is this a square root, but it's a square root that's in the denominator, so I say the denominator cannot equal 0. So if I combine these two things, not only does it have to be greater than or equal, but it can't be equal. So I'm going to take away that or equal to. So I'm going to say x minus 5, the radicand, needs to be greater than 0. So if we add 5, x needs to be greater than 5. So that's 5 to infinity. All right, let's go on to the next page. All right, so let's do some more examples. So example 1. I am not sure why that extra square root symbol is showing up. I don't think it's on your paper. All right, so example 1, this is just a square root. So since it's a square root, we say that that needs to be greater than or equal to 0. And this doesn't even have a denominator, so I don't even have to worry about that. So 3x minus 12 needs to be greater than or equal to 0. Add 12, divide by 3. So I get 4 to infinity. Okay, all right, example 2, this is a little bit different than what we've seen so far. So we have 3x over x squared minus 49. So if I look at 3x, that's just linear. That has no restriction. And x squared minus 49, that's just a quadratic. That gives me no restriction. But then I think about the fact that this is in the denominator. And because it's in the denominator, I have to say, well, x squared minus 49, we know that the denominators cannot equal 0. So x squared minus 49 cannot equal 0. So if you add 49 and then take the square root, one thing that we have to remember is that when you create a square root that's not originally there, you are going to create the positive and the negative answer. So what we're going to say is that x cannot equal positive or negative 7. So especially with multiple restrictions, the number line comes in handy. So here's 0, negative 7, and positive 7. So what I'm saying is don't be negative 7 and don't be positive 7. But everywhere in between is okay. Everywhere after positive 7 is okay, and everywhere before negative 7 is okay. So I'm going to represent this using my interval notation. So I can go as low as I want, but eventually I'm going to come to negative 7. I need to stop and skip that. I'm going to scoot this page over. Then I say, well, so now I'm right here. I'm saying I'm after negative 7. Eventually you're going to hit positive 7. And then you want to skip positive 7, and then you can go on forever again. So if you think about how this relates to your number line, this part of the interval, negative infinity to negative 7, that's like the space before negative 7. This middle is like the middle space between the two numbers, -7 and +7. That's what this represents. And this represents everything after +7. All right, let's go on to example 3. So square root of 4 over 9 minus x. Remember that when you have this big square root symbol, you would rather write it as the square root of 4 over the square root of 9 minus x, you can do that. And the square root of 4 is 2, but I can't do anything with the square root of 9 minus x. Alright, so this might be a little bit easier. If you look at 2, you would graph y equals 2 just as a horizontal line. That would give you no restriction. It's basically a polynomial because you're just graphing a straight line of 2. But this square root, we know it's a square root, so it has to be greater than or equal to 0. But it's also in the denominator, so it can't be 0. So now I'm going to have 9 minus x needs to be greater than 0. So you could solve this however you want. If you want to subtract 9, that's fine. You could do it a different way. If you want to divide by that -1 now, when you divide by a negative, that inequality is going to flip around. So now x is less than 9. So on a number line, here's my 9. I'm going to be less than that, so that's that way. So that's from -infinity to 9. All right, let's do example 8. So example 8, this kind of looks pretty similar. Oops. To example 2. My pen's not working. So we're looking at example 8. It kind of looks similar to example 2. Right? We've just got something on top. That would give us no restriction. Something on bottom doesn't usually give us restriction, but then the fact that it's in the denominator says, well, it can't equal to 0. So that's what I'm going to do here. Okay, so this has no restriction. But then I say, but because it's in the bottom, the denominator cannot equal 0. So I say x squared plus 16 cannot equal 0. If you subtract 16 and then take the square root, do remember that we have the plus or the minus, square root -16. But what happens with this? Can you answer me the question, the square root of -16? Even if you do know what the answer is, it's technically plus or minus 4i. When you take the square root of a negative number, it creates an imaginary number. It's basically saying it's not a real answer. It's just something that it's an imaginary answer. So this isn't really on the number line. If I asked you to point to this on a number line, it's not on the number line. It is an imaginary number. It's like your imaginary friend. It doesn't really exist, okay? So let's recap. We said no restriction, no restriction. The only thing that gave us a restriction ended up being imaginary. Therefore, this really has no restriction. So that's -infinity to infinity. Okay,